they both sample them. So when these two devices are speaking, for every byte there's an exchange. You cannot read a byte without also writing a byte, and you cannot write a byte without also reading a byte. And this becomes important when you begin reading the packet captures between them. Because when a byte goes over the wire, you need to understand exactly what that byte is saying if you're going to exploit the device or to capture something meaningful out of the traffic. And then once you've identified which pins and which rate and which protocol you want to use, you can stick hypodermic syringes into the board. These very quickly create a clean electrical signal with no soldering. Very few remaining marks will be on the device. This is a memory chip here underneath the laser. And then over to the left, this larger chip is a microcontroller. And these two are connected by an I2C bus, which is multi-master. And because it's multi-master, unless one of these chips is trying to hold the line open, you can connect to it as a second master, and you can just ask the memory chip for its contents while the board is still running. So in this case, I dumped the firmware that was contained within this memory chip just by tapping the two right pins on the top and having a regular I2C ROM programmer. You just run the commands out. You say, I'd like a contents of memory, please, and it gives it to you. You can use the bus pirate to do this, or I designed a board to do it as well called the GoodFET. And in either case, you just plug it in, you send the command to read the memory chip, and for I2C, it lets you. Now, to access the firmware, when it's held within an external chip, it's very easy to steal. But in the case of firmware which is held within a microcontroller, you have to use either JTAG or a bootloader. JTAG is a hardware protocol. There is no JTAG server application running within the chip. Instead, there's a hardware state machine. And the state machine allows for exchanges of bytes in a similar way to SPI. But it also has a state machine that you can wander through. So you go through different positions. There's one position that says you're shifting bytes into the instruction register, another that says that you're shifting them into the data register. And this is secured by either an EEPROM fuse, which can be attacked by ultraviolet light, or by a physical fuse, which is actually broken. And that requires probe needles. So this photo I took of Christopher Tarnowski from FlyLogic actually sticking a needle into a SIM card to tap the internal memory bus. And you can actually see the needle right here on the left. And this requires a lot of skill and a lot of equipment. But it's not necessary because you can use attacks on JTAG and attacks on the bootloader. You can do voltage glitching, which is where you just drop the voltage and bring it right back up. And if you do this very quickly, the chip cannot distinguish between this as an intentional attack and this as an accidental problem with the supply voltage. And if you do this at the moment that the flip-flops are latching in a value from a previous stage of the microprocessor, such as if you're fetching a value from memory, and the flash memory circuit is presenting that value in response to being given the address, and the value is about to be latched in to be, say, written to a register. If you glitch at that exact moment, the logic signals at that point will mess up, and the wrong ones will be latched in. This allows you to misexecute an instruction or to skip an instruction. So in the case of the MSP430, if you have a -1 or FFFF as an instruction, it does nothing. And you can force in NOPs like this by controlling whether the voltage is rising or falling at the instant that a loaded instruction is latched. You can also do a timing attack where you look for a piece of code that behaves differently, say for a correct password as for an incorrect password. And having found this, you run it both ways. And you have complete control over the chip when you're trying this. You can watch every bit of the output. You can watch the timing of that bit. You can vary your own timing to try to get the receiving chip to misbehave. So if they scrub timing after you present a password, you can actually gamble your serial traffic upon where the timing should be as it's listening. And then even if there's a delay between receiving a password guess and actually sending the reply back, you can still measure the timing of that guess. This is a BSL cracker, which I built to exploit a timing vulnerability in the MSP430. And you can plug this up to a vulnerable wireless sensor, and it connects through the upgrade serial port. Then it runs and it presents invalid passwords, just sort of iterating them until it figures out what each byte is. And they fixed the problem that this exploits and then reintroduced it again a model number later. This is a scope photograph of a voltage glitch. From here to here is half of a microsecond. And you can see the glitch occurs and ends within 50 nanoseconds. This is a recording of the power consumption of a chip. Once you capture a wireless sensor, you can knock the decoupling capacitor off of it. And I'm sure you've seen the side-channel power analysis attacks against smart cards. But this works differently in that you're not really trying to figure out what it's computing, so long as when it's computing it. Because if you want to glitch, you want to do it on one of these falling edges, which are the moments at which a clock edge occurs. Because on a clock edge, a CMOS transistor will flip. And it's only when a transistor is flipping in CMOS that it consumes power. In the case of the timing attack that I keep coming back to, if you have code like this, like if A does not equal B, then clear the allowed bit of the access variable. This format here where you do like and equals and the tilde to invert is very common in embedded C programming. But if you have this code, it takes longer to run if A does not equal B because it has to run that clause in the middle. And you can measure this. So on the left, you see the number of clock cycles that each simulation took to run. And you can see that some bytes, 00, 11, 3A, they completed faster. The difference of clock cycles divided by 2 gives you the number of times that those bytes occur within the password. If you see this password on the right, you'll notice that 3A occurs 15 times, just as predicted. 11 occurs 16 times, and 0 occurs only once. You'll also note that this password isn't very random. It wouldn't take you terribly long to guess this if you knew the general pattern. And the pattern is that every one of these words is an address in memory at which executable code exists. This is the interrupt table. So when the machine turns on, it looks here at this word, and that's where it begins execution. All of the unused variables have the same word in them. So if you were trying to brute force this, you could do it in very few attempts by assuming that the startup word, this 1100 here, always points to the beginning of flash memory, which on this chip is 1100. And then you just start counting up the other word until it latches in, and that will break any application that doesn't, say, rely upon interrupts for power efficiency or for button inputs or for things like that. If you have one that does use those, then you can guess which words will be outside of this pattern. And there are different strategies for guessing it. In a full application, guessing it becomes infeasible without the timing attack. But if you have an amateur programmer, or if the only purpose of writing the program is to test the timing of the password routine, then it becomes a lot easier. And you have further complications. You have a start bit. So in asynchronous serial, when you have an incoming byte, the line stays high and idle until that byte begins to be transferred. Then the line drops low for a single bit. That's called the start bit. And then the rest of the bits are sent least significant first. But if you look at the code inside the chip that's actually implementing this serial port, it will have a while loop that spins until the line drops